Dankeschön. Ich musste zuerst mal überlegen, in welcher Sprache ich den Vortrag gebe. Ich bin in Hessen geboren, also Deutsch lag relativ nah. Mein Arbeitgeber ist aber die European Space Agency und die hat zwei offizielle Sprachen. Das ist Englisch und Französisch. Und so English it is because je ne parle pas très bien français. So we will have that in English, and before I start, I would like to say I like tulips. So let's go about the space elevator. The space elevator is something very interesting because it is about abundance. Abundance of energy, of resources, and space as such as itself. It's really an unfailing well. There is no limit of what we can get from this resource, which is space. And what I would like to talk about today is our currently limited access to space and how we can improve that situation. It is the project to go from a dirt road to space to a highway to space, going from rocket to space elevator. And the space elevator has been thought about before by this famous guy. Arthur C. Clarke wrote a novel, it's called The Fountains of Paradise, in the 1970s about the space elevator. And in his book, he describes the potential of a space elevator. And so he was, for a long time, considered the main person to talk about space elevator. He was in Munich in a space congress, and he was asked by a journalist, so, Mr. Clarke, when do you think you will have your beloved space elevator? And Clarke said, well, we'll have the space elevator about 10 years after everybody has stopped laughing. So that's Clarke's story about it, but actually, we're currently 7 billion people on this planet, and we have a strong tendency to grow even further. I personally believe that growth and a big population is not really a bad thing. It's a good thing because we have more people, more brains, more ideas. However, it does create the problem of a lot of use of resources. And use of resources is a problem in the sense that, of course, on Earth's surface, resources are limited, but also their exploitation endangers our very existence by endangering our biosphere. So we have to find alternative ways to get to resources. And the interesting part is that we are actually bathing in a sea of resources. Just take the sun. The sun produces energy at the rate of 10 to the 26 watts. That it takes 2 millionth of a second to produce the energy that the Earth consumes in 1 year. So that's humongous. We have that very close to us. But also raw materials. There are companies today in the United States that try to attract money to exploit the near space resources. But there's a little dirty secret about that, and the secret is they don't know how to get there. And we today don't know how to get there. And more importantly, we don't know how to get those resources to the customers that are normally on the surface of the planet Earth. So we have to talk about space transportation, propulsion in space. And that works only with a very basic fundamental physics principle by Isaac Newton, which is action is equal to reaction. You can propel propel yourself in space only if you push against something, and that something is normally for a rocket is fuel. So as you exhaust fuel, and as you exhaust, you push it out in the mass you can push against, and that takes you out. And this is the basic principle of the rocket. It's a drawing by a very famous man by the name of Konstantin Tsiolkovsky, secondary school teacher in Russia. And he worked it all out. So he has a formula, it's called the rocket equation, and that tells you how to build rockets. So that's what we have today, rockets. That's everything we have today to build our space infrastructure. And this is an unmanned Ariane 5 launch, and you see that's a rather rough ride. You see all the flames, and also there's some risk involved in this, as you can see. And just imagine with those things, you actually cannot launch anything that is very sensitive or very big. And even worst part about it is it costs 20,000 euros to launch 1 kilogram into space with those things. But Tsiolkovsky was also a very smart guy, and he had not only the rocket in his repertoire, he was very creative, and he thought about a tower, because he visited the World Exhibition in Paris in 1895, and he saw the Eiffel Tower, and he said, what would happen if we would build this thing all the way into space? We can go all the way into space with a tower, and then we would be actually would have this momentum transfer through a mechanical structure, and we would not have to carry the fuel. And that would make it much cheaper. We only have to carry the energy to go up, which is much less in terms of effort. So that was Tsiolkovsky's idea to build a tower, and we saw this picture before about failed architecture today. It's nice to show things that fail, because then you can pretend you know better. Towers don't work. If you build them all the way into space, they would just sink into the ground because the ground's too weak. The Earth's crust is not strong enough to hold a tower that reaches all the way into space. So that doesn't work. And but what it does work, there's an alternative proposal to send a cable into space, let it down from space, just tie a little nice knot on the Earth's surface, and then you can climb that. And that's the idea of the space elevator. And let me explain quickly how it works. You have our Earth, and around it you have the nice geostationary orbit. That's the orbit everybody knows, where all the TV satellites are. You can put a satellite there, and it's just on top of one spot. It will stay there because it circles the Earth exactly at the same rate as the Earth rotates around itself. So the idea is now to have a payload on board the satellite, and that payload is a cable. So you can let down the cable, but you want to keep the center of mass at the geostationary point, so you let up also cable upwards. You keep doing that, and what happens is that, of course, at some point, the cable touches the Earth's surface. We zoom out a little bit, and we can see actually we have to extend the cable a little bit further than downward, because the gravity, as you go up, diminishes as you leave the vicinity of the Earth. How big is this thing? 144,000 kilometers if you have a balanced system. It's 1/3 the way to the moon, so it's rather long structure. You can leave the satellite, and then you can have a cabin, like a normal cabin. You attach it to the cable, and you have motors inside that get their energy from somewhere, solar cells, whatever, and you can drive up the cable. And that's how you get into space. There are many engineering problems to that, and most of them have been solved already. Interestingly enough, there's literature on that. There's one problem, though, that keeps us from having that beautiful structure, and that is the material. Because the weight of the cable itself would be so big, it would rupture under its own weight. The problem has partially been solved by a guy named Jerome Pearson in 1975, I believe. Yes, 1975. And he wrote a paper saying that if we make the cable thinner at the parts where we don't need a lot of strength, we make it thicker at the parts where we need to have the most strength, then we can make it, in theory, from any material. Interestingly enough, obviously, if you have a weaker material, you have to make it much bigger at the thickest point. And that's how he, this is not to scale, by the way, how he introduced this Pearson ratio or taper ratio, which gives just the ratio of the thinnest to the biggest point. Say if you have 1 centimeter down here, you have 100 centimeters up there, the ratio is 100. So let's talk about material. Of course, 20th century people will think, oh no, just different parameters I would like to talk about. So we have one parameter is the most complex one. It's called the rupture length. So that is the length of the cable you can have before it would rupture under its own weight. but that's in a constant 1G environment. Of course, we don't have a constant 1G environment. As you go up, G gets less. 1G means one Earth, how much the Earth pulls at us. As you go up, that gets less. But this is just theoretically, assuming you have a constant 1G, and you have a certain length. At this length, the material, depending on its strength and its weight, will just rupture. And the next parameter is the taper ratio that I just showed. And the last parameter is the weight of a cable, of a complete elevator cable, all the 144,000 kilometers of which that we would need to support a 100-ton cabin. 20th century people would, first thing, if you ask them what's a strong material, they would say steel. Let's start with steel. If you have 11 kilometers of steel, it would rupture under its own weight in a 1G environment. In order to build the full elevator cable from it, the thickest part would have to be 6 times 10 to the 189 thicker than the thinnest part. Expressed in terms of mass, that is, the mass would have to be bigger than the mass of the universe. Whatever. Doesn't work. If you ask us as 21st century people driving the latest BMW model, not mentioning other models, you would have to have a different material, and that would be carbon fiber. Carbon fiber is great because carbon fiber is lighter and is more strong than steel. So both make them about a factor of 30 better. So it ruptures only if you have it 330 kilometers long. If you build the whole cable from it with this tapering trick that Pearson invented, the factor is 3 million. You start with 1 centimeter, the biggest place up there is 30 kilometers. So that sounds already kind of, okay, well, space is big. We can put 30 kilometers somewhere. So it sounds scary, though, and it is, because the mass of the thing would be 1% of the mass of the moon in carbon. So that would be humongous. I would say that's not feasible. But there's stuff that we currently have in our labs. It's called multi-wall nanotubes. And this stuff we know, and we have experimented with it in the lab, ruptures if you have, under its own weight, if you have 3,568 kilometers of it. And the taper ratio would be 4. You start 1 centimeter, you go 4 centimeter at the thickest point. How much mass do you need to lift a 100-ton cable? 140,000 tons. So that sounds still like a lot, but however, 140,000 tons is roughly the mass of the cable of the Golden Gate Bridge. So that is something we can do in terms of industrial capability. But what about the realism of this stuff? Do we have multi-wall nanotubes? And if we do have them, can we make an elevator cable from it? This is a little video that shows how those things grow. It's taken from a scanning electron microscope in a chemical vapor deposition chamber filled with methane at 900 Kelvin. Now I've given you the recipe, you can do it yourself at home. So this sausage-shaped thing is a substrate, aluminum oxide, and you have nickel particles on it, the black things. And see what happens if we roll the movie. You see in this red circle that is created by me, not by the microscope, you see a little sock growing like a crystal structure out of that catalyst, and that is a carbon nanotube. So we can watch them grow. They grow at the rate of about 50 to 100 micrometer per second. So that's roughly a tenth of a millimeter per second. Not very fast, but you can have many of those catalysts, and then it works much better. But we can grow obviously more than one. We can grow a full forest of them, and that's what you see in this picture by Chang et al., where you have a full forest of them grown to a height of about 30 microns, and if you pull one of them, you can start spinning. So you can combine 21st century technology with 9th century technology and put it to a rope, to a cable. And interestingly enough, if you pull them out, the neighboring nanotube would pull its neighbor out into the thread and if you spin it, it would just be infinite. To show you that this is not some crazy picture stuff that is for real, that's a movie by the Rice University, Houston, Texas, and they have spools of this stuff. Spools full of cables made of multi-wall nanotube. And you see a student who lifts a heavy steel cylinder with a thread made of this stuff. But you can also see, if you watch with a critical eye, he is not having something that is thin as a hair. He's having a big thread to maintain this thing. That already shows you that there is still work to be done, because the rupture length of this stuff that they make in Rice is only 100 kilometers. Why is it so short? Well, we take 50 micron short fibers and spin them into an infinite long cable. Now, if you pull, what happens is you're not rupturing those carbon nanotube fibers because they're extremely strong. You're pulling individual fibers apart. So all we have to do is to make this contact surface bigger, because the force to pull two apart is in proportion to the contact surface. And how can you make those bigger? You make longer fibers, and then you can twist them even more, and the contact surface grows in proportion with the length of the fibers to some point to which you can actually need more force to pull two apart than you would need to rupture one. And then you will have achieved a very interesting feat. And so this is still not good enough, but there's a group in Beijing, Wang et al. Published that a couple of years ago, and they grow ultralong. They have a method to grow ultralong carbon nanotubes, and they grow them for their electrical properties, not for their mechanical properties. And the reason is because they want to make nano transistors from that. How long is this stuff? It's 18 centimeters long. Not a millimeter, not 1 centimeter, it's 18 centimeters. So my proposal would be to use this technology and implement it in the spinning way that I showed before and have a strong cable. And once we've achieved that, we can transfer this enormous strength of the nanotubes to the enormous strength of a rope, of a cable that we can use to build the space elevator. And then suddenly we'll have the capability of launching stuff for 2 orders of magnitude, one factor of 100 less than we use today. And we can build structures that will allow us to just go out and harvest this unlimited source that surrounds us. We can build structures not in kilometers in size, but thousands of kilometers in size. And we can build stuff like that. This is from the NASA study from 1999, it's called CERT, collecting solar energy, not when the sun shines, because in space, the sun always shines. And then we have suddenly achieved a feat that makes us much stronger as a species. We will have beaten the limits of growth, like predicted by the Club of Rome, and we'll be able to build anything, any structure. We'll be able to build bases on the moon, hotels on Mars. We can build big civilization ships, habitats that host thousands of people, and then we will have finally achieved an ancient dream of humanity to become really a spacefaring species. And then I think we have to solve only one more problem, and that is how to find elevator music that you can bear on the 4-day trip. Thank you.